This is lab report number 3, concentration gradient and entropy.
The purpose of this experiment was to devise a system to observe and analyze the motion of beads under a microscope to affirm the presence of a concentration gradient and other entropic principles.
A key concept underlying this lab is entropy. The beads added into our system will be influenced by diffusive motion and are moving down their concentration gradient, that is, moving from an area of high concentration to low concentration. This is related to entropy, as energy will tend to move so that it is equally shared among all places in order to maximize entropy in a system. Entropy is defined as the amount of randomness and energy dispersal in a system, and it is always increasing in the universe. In our case, when the beads are equally dispersed, maximum entropy has been achieved, and the concentration gradient is equal to 0. The concentration gradient formula is as follows: change in concentration over change in distance. You can alternatively find the change in entropy by multiplying the natural log of the microstates by kV. However, there are infinite microstates present in the system, so concentration gradient serves as a more feasible method. Yeah. Maybe we can do it.
Oh, okay, I think I got it. All right. Oh, it's recorded. Using tape on a microscope slide, a small channel was created and a drop of polystyrene bead solution was placed in the channel to track the bead's diffusive motion and subsequently the concentration gradient. A cover slide was used to encourage diffusive motion. Tracker was used to focus on a portion of the large channel, which was subsequently divided into 4 smaller channels, as this would provide us with multiple measurements. To determine if concentration gradient was decreasing over time, we took 3 screenshots, one at the beginning of the start of flow, one in the middle of video, and one in the end. We were able to investigate if entropy was increasing as time progressed by calculating the concentration gradient in each vertical column at 3 different time points. At each snapshot of time, we calculated the concentration gradient by dividing the change in number of beads by the change in the width of each column. From there, we took the average of all the concentration gradients in that point in time. We also took the standard deviation to calculate any variation and error in the concentration gradient of each channel at that time point.
At the beginning screenshot, the average concentration gradient was 0.311 with a relatively large standard deviation of 0.24. This deviation could likely be attributable to the quick flow of beads, as the screenshot was taken shortly after the beads were dropped in. The middle average concentration gradient was 0.233, and the standard deviation was 0.129. The final end screenshot had an average concentration gradient of 0.138 and a relatively small concentration gradient of 0.047.
Movement of the beads were also visualized using graphs. As time progressed, we would expect the slope to flatten as the concentration gradient reaches 0. A slope of 0 would indicate maximized entropy, but this was not achieved. By the third frame analyzed, the number of beads in each channel were relatively similar to the other, the slope was flatter, and the concentration gradient was closer to 0. During the beginning and the middle of the flow, there were more beads in channels 1 and 2 than in channels 3 and 4. This was expected, as the beads need to cross the first 2 channels in order to reach the second 2. The slope is much flatter in the second graph than the first, as the beads attempt to reach equilibrium. At the end of the flow, the suspension completely stops moving. This is when maximum entropy should be reached and when the beads in each channel should be equal throughout. Although there are minor discrepancies in the graph, it seems as if an equilibrium is most established here. Maximum entropy was not reached because concentration gradient never equaled 0. However, the entropy increased over time because the concentration gradient got closer to 0 over time. It is worth noting that the largest standard deviation was pulled from the beginning of the diffusive flow and decreased at each point in time measured. We believe that the variation in the data was small enough to conclude that, while there was error present, the concentration gradient was decreasing over time. Multiple types of systematic and random error could have been present in the experiment. Because all beads were accounted for via human eyesight, it is possible that beads were completely missed or counted more than once, which is a random error. Another form of random error would be someone bumping into the table and shifting the movement of the beads, which could influence the concentration gradient calculations. Additionally, our microscope was slightly out of focus, which could be classified as a form of systematic error since it impacted bead counting each time. This concludes Lab Report 3.